PhD student in the cryptographic group at TU Darmstadt, and her research is focused on provable security for real-world protocols. In particular, she's interested in wireless communication protocols, which require active user involvement for security. So on that topic, she's going to be telling us about her recent work of analyzing Bluetooth, as well as some security enhancements to its key agreement protocol. Now, somewhat surprisingly, given its prominence, but also its age, Bluetooth is not a very secure protocol. And this is interesting given how much infrastructure that relies on it, especially recently with the move towards wireless everything. So I was recently told that modern-day race bikes actually use Bluetooth to connect between the brake handles and the disc brakes. So this makes this protocol crucial not only for security, but also for personal safety. So with that, I want to hand it over to Olga.
Thank you for the introduction, Matilda. So I will go right to the disclaimers. Even though this is the joint work with my supervisor, Mark Fisher, and the opinions that I will present are only my own. And I will also present you some attacks and mention them, but this presentation is only for the educational purposes. So the question that I often get is, why do you analyze Bluetooth? Because it's so old. So first of all, I didn't want to analyze TLS and to be yet another one who's analyzing TLS. And second, Bluetooth is really everywhere. There are 8 billion devices and the number is only increasing. So from the user perspective, Bluetooth works like this. Assume you have a laptop and a phone and you want to connect them, and then there will be some digits displayed on the screen. Now, if you have something like the headphones that do not have any screen, but you want to still connect them with your smartphone, then you do not have any digits displayed, but you will have some menu displaying that there is a connection going on in the process. Now, Bluetooth is actually a big protocol stack, so whatever you see, the digits, it's just one of the protocol. And this is the top of the iceberg. There are many more protocols in the stack of Bluetooth, and I will look more into details together with you in a second. So there are 2 main types of Bluetooth transport. Bluetooth low energy that is used in your smartwatches when you want to send the signal only periodically, and there is Bluetooth classic that is used in more continuous data transfer, like when you're playing your favorite video game. So they both start with discovery of the devices, and this works similar to how do you discover the Wi-Fi networks. Then they also discover some of the capabilities that they have, and the first protocol that they had in Bluetooth is now called Legacy, but before that it was pin-entry. So spoiler alert, this protocol is not secure because it was possible to just brute force the pin and then get the key. So as a solution, the special interest group suggested to have secure simple pairing or secure connections protocol. This one implies elliptic diffie Hellman, and it's more secure. In Bluetooth low energy, they have exactly the twin sibling of this protocol. And funnily enough, they also have something that they call secure simple pairing, but this is a weird mix between legacy and secure connection protocol. So they try to mimic secure connection, but it's actually not secure even against passive addressers because you can always brute force the pin. Now you might think, okay, we are done, Bluetooth is done, but no, this is not where it stops. We just derive the long-term keys or link keys here. So what we do next, we derive the encryption keys and we authenticate the devices. And in Bluetooth low energy, you have one additional step to distribute the keys. Now the idea behind secure connection, which is the most secure protocol in the stack, is the following. It's just as any key exchange protocols. You have an insecure channel and you want to make a secure one out of this. So you need to derive a key. For this, you need to run authentication besides the key exchange. Problem, in Bluetooth, you do not have any public infrastructure. So what you're going to do, let's involve the user. So you assume that there is a secure channel between the user and the device, and the user can either enter the digits or confirm that they're the same. But the problem is that not all the devices have the screen or opportunity to display or enter the digits. So you want to have more protocols, and this is what Bluetooth did. Problem, they also negotiated over the insecure channel, and again, spoiler alert, it's not authenticated. This choice is not authenticated. Another problem is that this choice is not clear for the user. So the user does not know what exactly protocol the devices will be using, and I will show you in a minute why is it a problem. So from the high level point of view, secure connection protocol works as following. You connect on the physical level, so you exchange your MAC address. Then you exchange your input-output capabilities, and you agree on the protocol that you will be using. In this case, this is secure connection. So it works as following. You exchange the public shares in elliptic curve Diffie-Hellman, then you exchange the nonces, and then you confirm the transcript that you derived so far. Then you derive a link key or in Bluetooth Classic or long-term key in Bluetooth Low Energy using the MAC addresses, the elliptic curve Diffie-Hellman shares, and the nonces. So input-output capabilities are not included into the KDF. Now for reconnection step, it might happen that you disconnected, so you need to rediscover your devices once again. If you do this, then you can establish the session keys. What you do for this, you exchange some challenges like nonces, and then you use this nonce together with the link key or long-term key to derive the encryption key. And exactly this key will be used for encryption of the data. So link key or long-term key is just stored there, but is not used for the encryption. This is very important. Now you might wonder, okay, it's been for a while, so for sure people analyze Bluetooth protocol stack. You're correct, so there were already some papers that analyzed, but the problem is that they didn't model the protocol close to the standard, meaning that they did not assume that only X coordinate is entering the KDF function. Now, Troncoso and Hale did this correctly, but they did not assume that the same Diffie-Hellman share can be used in multiple sessions. So I don't know what was the choice behind these research papers, but I might say from my point of view that analyzing Bluetooth is really, really difficult. And why is that? First of all, you have a standard that is 3,000 pages long and 800. And somewhere you might notice, oh, actually the devices should change their keys every 8 connections. Then, if you want to analyze Bluetooth Low Energy, then you need to skip 600 pages and find the part where Bluetooth Low Energy is described, and there you see, oh, only X coordinate is used. Now, you might think, okay, I'm smart enough, I will just search for authentication, and then you will get 900 entries of the authentication in the document. And what we as a community understand as authentication is not what they understand as authentication. So you might have seen this slide from the real world crypto this year, when Tushar Joyce showed the relation between security community, cryptographic community, and the low layer standard bodies. If you add security community here, I think the picture would look even less. It's like even worse. And why is it a problem? Because there have been some attacks in the security community that we did not see in our cryptographic community. So for example, there was an attack to reduce the size of the encryption key to 1 or 7 bytes, and this might be problematic for the proof. Now, there have been also some attacks to replace one protocol with another one, and the worst case is that there is a black sheep in the whole protocol stack, which is called just works, and this is plain Diffie-Hellman key exchange. And you can always downgrade to this Diffie-Hellman key exchange protocol. There have been also some attacks on separate protocols, like you would manipulate the passkey entry, or you would manipulate the devices so that they think both of them are initiators. As I mentioned, there was also an attack on legacy, that it was easy to brute force the PIN that is used for authentication. There have been surprisingly an attack on invalid curve, where you would replace the Y coordinate of your public key share with 0, and this would allow you to brute force the key easily. So this leads us as researchers to some assumptions that we need to have, meaning we assume in our analysis that always the maximum size of the key is used. Then we assume that the legacy protocol is disabled because there is no security guarantees that we can have for legacy protocols. It's not even secure against passive adversaries. Then the best we can hope for is the plain Diffie-Hellman security, so it means that the best we can get is the passive security. Finally, we assume that the Y coordinate is checked, so you cannot replace one curve with another one. Now, the result that we got in the first paper is the following. We included all the secure connection protocol stack in the family, and we analyzed them in the trust and first use model, meaning that whenever you have the adversary eavesdrop on the initial connection, you can only have authentication guarantees later on in the reconnection step. So the adversary can be active only during the reconnection step. Now, the properties that we aim for are super basic. It's just key secrecy, so the key is indistinguishable from a random string, and mesh security, that the two partnered sessions derive the same key and run not more than 2 sessions like this. We had to adjust the capabilities a little bit of the adversary to address what can be done in Bluetooth, meaning we added 2 more oracles to initiate the session depending on the type. This is just for the administrative because it's much easier to model this way. Then we modeled the next PK, and this is the oracle that allows the adversary to choose when exactly to replace the next key he haven't shared. Now, we did not model any corrupt oracle because there is no long-term keys in Bluetooth. Now, you might think, okay, we can corrupt the long-term key or the link key, but if you do this, then there is no security guarantees because always the link key or the long-term key will be used to derive the encryption key. So if you corrupt this, no connection following is secure. So once again, what do we have? We have initial connection, and the adversary can be passive during this, and we have active adversary during the reconnection step. Now, a natural question is, can we actually do better? And we, as researchers, always have some choice to do. We can either design a completely new protocol from scratch, or we can try to fix the current one. This is what we chose, and this is more challenging, so that's why we also chose this. So let's see, there have been some new attacks on Bluetooth that can be reported, but not all the attacks are making it to the report system. So this is how it was in 2021, and this is how it is now, or maybe there are even more attacks. I didn't check actually yesterday. So some attacks are just extending the current ones. There have been some attacks that we still need to acknowledge in our research, meaning there is a special transferred key derivation function. If you connect on the Bluetooth low energy and you want to still be able to connect on Bluetooth classic, then you derive a special key for this. But this procedure is not secure, so what we had to assume is that this procedure is not used. Then there is, again, a surprise, a reflection attack similar to selfie attack on TLS in Bluetooth. So whatever is received will be just sent back by the adversary, and then the device will accept this connection as a secure one. So we also had to assume that the check is going on, and this is not possible to do. Now, the fix is actually not that easy as you might think. First of all, you need to find something that will acknowledge all the attacks that are already there. And problem, you want to still have the backward compatibility, because whenever you have a new device, new Bluetooth version, you do not want to get a new device for this. Meaning that we cannot introduce any changes in the protocol, and even worse, Bluetooth devices are constrained, so it means that we do not store any transcript, so we cannot use transcript and just sign it. But still, you want to do a little bit better than TOFU, so trust and fast use, and what you can normally do is to have out-of-band communication, for example, QR code or NFC. But not all the Bluetooth devices are supporting this, so it's not a good option. You can have something similar, like it's done in Signal or WhatsApp, to check the QR code that derived. But again, not all the devices have screens in Bluetooth, so you still need to have something better. Another solution is to have just pre-shared key, like in TLS, but this is exactly the setting of TOFU. So you derive the link key or the long-term key, which is secure against passive adversaries, and then you can use this key to protect against active adversaries in the reconnection step. So what we thought, let's use cryptography, so let's run additional authentication step on top of Bluetooth. So we decided just to add signatures, meaning that if we have 2 devices, we just assume that each of them also have a certificate and linked keys to this certificate. So both devices will generate a challenge and exchange this challenge, and then some authentication data will be computed using the challenges and the link key and the long-term key that they're sharing. Then Bob will sign this authentication data with his own secret key and send it back to Alice together with the certificate and the public key, and also the challenge that was not sent to Alice so far. Alice will also compute the authentication data, and then she will check the certificate and the received signature. So far so good, but if you want to have mutual authentication, then you need to have the same protocol run with the reverse role. So now Alice will authenticate herself towards Bob. Now our solution links the long-term key links authentication to the long-term keys, and this is nice because we do not need to have any other additional information on this. We use existing functions, so you might see that we used HMAC and Bluetooth Low Energy, it would be CMAC, and we used all the functionality that's already available in Bluetooth. So we did not design anything new. This protocol can run at any point of time. And this is nice because sometimes devices in Bluetooth can just disconnect. Maybe they ran out of battery or the network communication was not good enough. So they will just disconnect, but this is good because we still can run the authentication protocol at any point of time. So we suggested 4 schemes in total, and the reason is that we need to have separately protocols for Bluetooth Low Energy and Bluetooth Classic, and we also added Diffie-Hellman-based authentication scheme in case you want to get some privacy. Now, how it exactly works is the following. In TOFU setting, if you run the initial connection, and this connection was TOFU secure, this means that all the following reconnections were secure until the next initial connection. So if this one was again secure against passive adversaries, then all the following reconnections were also secure. Now, with authentication, it means that also the previous connections were secure. So it's not only the future ones, but this way you also make sure that the link key or the long-term key that you derived was not modified by the adversary, and this is exactly the person that you're talking to. Same here, you run authentication, then all the previous connections are secure, and also the future ones. Now, we managed to thwart some of the attacks, but not all of them. And the reason is, again, legacy protocols, there is nothing we can do against them. Some attacks, like reflection attacks, this is not something that we as researchers need to check, but rather implementers need to check. So the result that we had is following. We just took the TOFU model that we already had, and we added authentication there. We managed to prove that Bluetooth Classic provides the security, but we failed with Bluetooth Low Energy. And the reason is that Bluetooth Low Energy uses CMAC as a key duration function. Now, if you want to know more why is it not good, why collision resistance in CMAC is possible, check out Matilda's talk during Eurocrypt, and hopefully she will tell us more about this. So we introduced 2 more notions for this authentication, which is pretty simple. You make sure that you're talking to the party that you want to talk to. And leakage resistance. What does it mean? It means that the authentication data that we are computing does not leak any information about the link key or the long-term key, because we're using these keys to authenticate, right? Now, instead of a conclusion, I will just show you some statistics. So if you search for TLS on ePrint, then you get 85 entries. If you search Signal, then you get 32 results. Guess what you get if you search for Bluetooth? You get only 18. And we as a community can change this. So you might know the story about mice who wanted to know when exactly cats are coming. So they wanted to put some bells on these cats. And guys, the bell is already there. So if you want to know more about Bluetooth, check out our papers. It's really accessible for cryptographers, so you can get easily into this protocol. And if you want to do something like authentication, as we did, or improve Bluetooth protocol, then you can use our second paper as the example. So this concludes my talk. Thank you so much for the attention.
Thank you, Olga, for that excellent talk. We have a lot of time for questions, actually. So, is there any from the audience? Yes, ma'am. Just go ahead.
The authentication protocol you used kind of looked like Sigma. Is there a reason you came up with your own? Is Sigma overkill because it derives a new key for encryption and you don't need that key, for example?
So I must say we wanted to try to not use cryptographic solutions for this and use something like you use a pin in the headphones to listen and use this pin as the pay. But nothing worked out. We tried to disable some protocols in the SEC, like JustWorks, that is only secure against passive adversaries, but this also does not work because there is still attacks between the protocols. So the best we can think about is just adding signatures. This is just a really Sigma protocol. But why did we come up with our own is because we wanted to make it backward compatible. So we wanted to use functionalities in Bluetooth. They have their own like F5, F6, and so on functions. So we wanted to use exactly those because that would be easier for implementers to have.
I see.
So this is not a complicated protocol, you're right, like this looks familiar.
It's compatible, okay. Thank you.
Any other questions? Yes, please go ahead.
Thanks for the great time. This is like really amazing work, and I'm just like wondering, do you communicate with like Bluetooth community on these things, or like how do you proceed from?
This is a really good question. So we try to communicate with Bluetooth special interest group. This is like a standard body like Signal has, for example. But they're not really, let's say, responsive to the community. If they really see the threat in the security, like if you run the practical attack, then they will put it on the website. But if you say something theoretical, like guys, from the theoretical point of view, your protocol is not secure, they will not answer to you. Or they will say, like, we will come back to you. So we did not have really good experience with them. And from other Bluetooth researchers, I know that they also did not have really good experience with this, unfortunately.
And like when you kind of had all those attacks on the screen, how much of them are like actually like really easy attacks to do in the real world compared to like more theoretical kind of attacks?
So I gave a lecture to students at the master level, and they were amazed how easy these attacks are. They also, I don't know how easy they are to launch, because I'm not a practical person, right? I'm more from the theoretical point of view, but there were some attacks that were also tested against real devices, and it turned out that these devices are not secure. So it's possible to run some of the attacks, but I don't think all of them, as far as I remember.
Okay, any more questions from the audience? Are there any online questions? No? Maybe I'll ask a quick question. You said you had the choice, right, of the two red buttons between redesigning and fixing the current protocol. If you had instead chosen to redesign Bluetooth, what would you have done?
Graduate with my PhD first, so that I have more time to do this, and more confidence to do this. I think I would just like erase everything and literally design it from scratch. Literally, like everything deleted.
Would you be using some of the protocols that we have already, like, you know, TLF, for example, would it work, or does it really need to be its own thing because it's too different from its assumptions?
Oh, that's a good question. I think you might use existing protocols, especially if you want to use certificate-based authentication. And Bluetooth actually supports this because there are newer versions of Bluetooth that have this. But this is again tricky because Bluetooth is a really low-layer protocol. So it doesn't run on an application layer as TLS, but you have some really down things that you need to acknowledge for. So maybe you would take something like TLS as a basic of it, and then you will try to adapt it to the Bluetooth reality. Maybe this should work.
Sounds like an interesting problem. Let's thank the speaker again.